All right, we're going to go through how to solve an air resistance problem where the air resistance depends on the velocity. And to do this, we're going to have to use calculus and use some new techniques some of you might not be familiar with. So if it's a little bit confusing, that's okay. You'll have time to go back over it again. And we're going to see when we get through a few of these problems that we don't always need to solve the calculus problems, that if we notice some trends or some patterns in them, that we can actually predict what the solutions will be, and we can use our result of solving a couple of these to get solutions to other ones without going through all the calculus. So don't get too scared. But anyway, here we have a car slowing down under air resistance. There is no force pushing the car forward. It says the engine shuts off. So it's just a car that has an initial velocity and is slowing down under air resistance. We're also going to assume here, since it's our first problem, that friction is negligible, although in real life it probably would have some friction in this situation. So we're going to start just like any other force problem by drawing a free body diagram. So there's our car. I'm going to assume has a velocity to the right, and it would have a normal force acting on it, a gravity force acting on it, and it would have this air resistance force. We'll call it FR for F resistance, opposing the direction of motion. And that's it. And for our situation, we're really just concerned about the x direction. Let's just say up is positive y, to the right is positive x. Again, we're really concerned just about the x direction, because in the y direction, we already know from other problems, normal force. In this case, it will equal to the gravity force, but because there's no friction, it's not going to really give us anything useful. So I'll start by writing a sum of the forces equation in the x direction, where we have just a air resistance force in the negative direction, and that's going to equal m times a. Nothing new. Now, to get started, we have to write what we call a differential equation, and all we're going to do is take our Newton's second law equation and write the acceleration in its differential form or its derivative form. We're also going to sub in, it tells us that the air resistance force can be represented or modeled by negative k times v, where k is a constant, so we'll sub that in for the air resistance force. And this just turns into negative kv equals m, and then we write our acceleration as dv dt. And there is a differential equation. Again, doesn't look too scary yet. Now we're going to rewrite it a little bit just to make our life easier. We're going to do something called separation of variables, where we take our differential equation and we group the terms that go together. So in this case, we're going to group the dv and the v terms together on one side and put all the other terms on the other side. And we're going to get something, again, another thing called a differential equation with the variables separated. So this turns into, we'll bring the mass to the left, we'll bring the v to the bottom on the right, and then we'll bring the dt to the other side, and we get something that's of the form negative k over m dt equals dv over v. And this is just our kind of cleanup for, or not our cleanup, but our modified version of our differential equation. But really, this is kind of our differential version of our Newton's second law equation. So far, not too bad, just writing it a little bit differently. Now we want to derive an expression for the car's velocity as a function of time. Now this is where it gets a little bit difficult, because we notice that we do have a velocity term down here, but we also have the dv term in here, and we have a dt term over here. We want to just get velocity as a function of other things, as a function of time. To do this, we have to take an integral. So if I'm going to kind of expand this, let's come down here. We're going to integrate negative k over m dt, and we're going to integrate the other side, dv over v. Now to do this, we're going to use a kind of a couple little sneaky tricks here to get what we want. So our problem is starting from time equals 0, and it's going to some time in the future. So I'm going to integrate my time from 0 to just some time t. This is going to it's a little trick that's going to give me any going to allow me to get any constants I need or anything like that out of my system or out of this integral. And if I'm integrating my time from 0 to t, I have to integrate my velocity over those same points in time. So at time equals 0, my car has an initial velocity of v naught. So I'm going to integrate my velocity from v naught to some v at whatever time t ends up being. So the v and the t are kind of like the open variables that I'm kind of getting in here. They're going to be changing over time. And the 0 and my v naught are my initial conditions. So now at this point, one side of this equation is very easy. The integral of some constant times dt is just that same constant times t. So the left side here simply becomes from 0 to t, negative k over m dt. That's just using the power rule where the initial power is 0. We can do that. Now the other side gets a little bit tricky because we can't use the power rule for something that's divided by v, but there is another known solution to an integral in a situation where the integral is d variable over the variable itself, and that is that the solution to this is just the natural log of whatever that variable is. So in this case, it's a natural log of the velocity. Now again, this your calculus teacher can go through the long version of that, but that's a very well-known solution to this integral. So we can just use that because someone else did the hard work for us. So from v naught to v, it's being that of the natural log of v. Now some might say this is even worse than before because this is having natural logs in here. A lot of us don't really like those in there, but we're going to see it's going to become a little bit easier. There's another trick we're going to use in a second that lets us solve and get rid of that natural log pretty easily and get a really nice solution out of this. But first, we have to put in our limits of integration here. So actually, just put a dt there. It's just a t. So for our time term, when I put in 0 for time, that's just 0. So really the first term here just becomes negative k over m t. The other term becomes the natural log of v minus the natural log of v naught. And there is one more trick we can do with natural logs where when you have the natural log of something minus the natural log of another value, that is equal to the natural log of those two values divided by each other. So this is equal to the natural log of v over v naught. So we're actually, it seems like this is a little bit scary, but we're actually almost done. Let's bring this down here for a second. So again, we got negative k over m t equals the natural log of v over v naught. Now to solve this, it seems like it might be difficult to solve. How do I get the v naught out of there? I got natural logs. But again, we can use another little sneaky trick. We're going to, I don't know if this is a word, but exponentiate all these. We're going to just take and make both sides become e to whatever that thing is. So I'm going to make e to the left side, and I'm going to do the same thing and raise e to the power of the right side as well. Again, it's an equality. If I do the same thing to one side, I can do the same thing to the other side. It still seems true, but now something really nice is going to happen. When we get the left side, just stays e to the negative k over mt. The right side, though, e to the natural log of something cancels each other out because e and natural log are kind of inverses of each other. So this now becomes e to the negative k over m t equals v over v naught. And now we have our v. We almost have it by ourselves. We just got one more step. We're just going to bring our v naught to the other side, and we get that our velocity as a function of time equals our initial velocity times e to the negative k over m times t. There's a nice solution for our velocity as a function of time. Let's go through and just check and make sure our initial conditions work. At time equals 0, e to the negative k over m times 0 is really e to the 0. Any number to the 0 power is 1. So our velocity at time equals 0 is our initial velocity, so that works. And this thing should stop over a long period of time. It's moving, it has a force opposite motion, so it should stop. So at a large time, if we say t goes to infinity, we have e to the negative k over m times infinity. So that's really e to the negative infinity. Anything in negative infinity power equals 0. So our velocity after a long time goes to 0. So there's the first part. Not too bad. Now let's move on to the next question. It says it wants us to find an expression for the car's position. Well, we know that position is the integral of the velocity function. So we have a velocity function here now, so we can use it and we can take the integral. So let's say our position as a function of time is going to be the integral of our velocity as a function of time with respect to time. And again, I'm going to go from time 0 to time t. So this is an integral from 0 to t. And I'm going to sub in my newly found equation up there of the initial velocity times e to negative k over m t dt. And now this is kind of nice because the integral of e to any to something is e to that something. We just got to worry about pulling out our constants. So this becomes, let's pull out our initial velocity on the outside. Now, when you take the integral of something of e to the some power where there's another constant inside here, we have to then take, there's a thing you might have learned in calculus called the chain rule. We have to take the derivative of that thing that's inside of there, or the integral of that thing that's inside of there. So this ends up becoming, so we have to divide by, when we take the integral of this, we have to divide by that term inside there. So we're going to get, dividing by that term inside there is the same as multiplying by its inverse. So I pulled my v naught out. We have negative m over k. That comes from dividing out the term inside there. And then we just have, we're left with e to negative m over kt. Or e to negative k over m t. So this is, again, another one. That doesn't look too well. K over m t. This is another one of those integral identities that you learn about in calculus. Again, this is from time equals 0 to time equals t. Now this gets slightly different this time. So if we kind of do out our limits of integration here, we end up with, let's see, we can pull out v naught, negative v naught, m over k out in front. And then we have, let's see, t for time and then 0 for time. So we have e to the negative k over m t minus e to the negative k over m times 0. So there are my limits of integration after pulling out the constants. And now e to the negative k over m 0 is really just 1. So this turns into, let's see, negative v naught m over k times e to the negative k over m t minus 1. And that looks, oh, we can do one more thing. We have a negative in the front here. We have a negative 1 inside there. Let's multiply the, let's bring a negative out. So let's write this a little bit cleaner. And in our final version, we should get our position as a function of time is going to be v naught m over k times 1 minus e to the negative k over m t. All I did was I kind of pulled out a negative 1 from inside of this, and then negative 1 times negative 1, got rid of the negative in front just to make it a little bit cleaner looking. And there is our function of position as a function of time. Now, what we can do with this is, let's do it again. We want to do a check to make sure that it kind of matches what our initial conditions are. So we know that at t equals 0, our position should be 0. So if I put 0 in here for time, this second term here becomes 1 minus 1, which is 0. So our position at time equals 0 is 0. So that makes sense. At time equals infinity, our position should be some value. It's actually our max value because that's when our car stops. So if we put in infinity in there, we get v naught m over k times 1 minus and e to the negative k over mt goes to 0 because it's negative infinity. So our position at infinity is actually, this is something we could figure out, is just v naught m over k times 1. So our initial conditions work. So we have our equation for our position as a function of time. Next wants us to do a couple sketches. It's to sketch the car's velocity as a function of time and the car's position as a function of time. So these are both exponential functions. Now, exponential functions, sometimes you might forget what they look like. That I like to do is look at my bounding conditions, my time equals 0 condition and my time equals infinity or over a long time condition, and see what they do. And I always know that exponentials kind of asymptote at some number, either asymptote at 0 or asymptote at some number. So when I know what they're doing, I can tell whether it's going to kind of curve up an asymptote or curve down an asymptote. So my velocity has a velocity in the beginning. So initially I start off with some velocity v naught, and then it goes to a velocity of 0 over a long time. So this is, let's say, v naught up here. I know this is going to asymptote and curve down and eventually flatten out. For my position, it starts off at 0, and it eventually reaches some position x max, which we just found was v naught m over k. So if this, let's say, is x max, I know that this is going to curve up an asymptote over some time at x max. And the last part we actually already did. It says determine the displacement of the car from t equals 0 to t equals infinity. Well, we just kind of did that. You can do that fully. So again, we have our position as a function of time, and we want our position at infinity. Our position as a function of time is v naught m over k times 1 minus e to negative k over mt. And now we want to do this at infinity. So this is v naught m over k times 1 minus e to the negative infinity. Well, e to the negative infinity is 0. So this just turns into v naught m over k, which is what we saw above. So that's our simplest case for using air resistance, where the only force acting in our object is air resistance, and our object had an initial velocity that slowed down to 0 over some time. And this kind of tells us how long it would take, or what's going to happen to the velocity and what's going to happen to the position as this thing slows down over time.